very kindly advertised. This is maybe viewed as a complementary view of how the melt-pond geometry can be produced. But this model is actually more based on physics. So I hope it provides you with some complementary views about how this geometry came about. Okay, what's this USB thing? Okay, so that was black screen. Should come out. Okay. Yeah, okay. So that was for the laser point. I have to do it in the right order, yeah? Right. Okay, there we go. Thank you. Okay, so what's the main goal for the talk? As of today, or maybe not for much longer, these two geometric features have not been quite understood. One is the power law scaling of this melt-pond distribution. The other is critical length scale, where these melt-ponds undergo a transition in fractal dimension. So here we will introduce a more physical model, which is known as the two-dimensional random field Ising model for melt-ponds. So actually the main aim fits into the scheme that Ken talked about on Monday, which is to link the scales. We want to link the microscopic scale to the macroscopic scale. And in doing so, we'll have found a way to explain these geometric features. Okay, so these are some pictures of melt ponds. So we have seen this many times. So during this melt season, this Arctic sea ice cover becomes a very intriguing looking mixture between ice melt pond and open water. The left picture is in mid-July, right picture is in mid-August. So as you go further into the summer, this pond get more connected. So this was taken in the western Balfour Sea, which I believe is near the Arctic Circle. So there are huge relevances between these melt ponds and the climate science in general. This melting is an important phenomenon which is strongly influenced by the geometric characteristic of this ice cover, including the pond area and perimeter. So there's a very important feedback effect which climate scientists talk about, is the ice albedo feedback. So as you melt more sea ice, you have lowered the albedo because more water appear, and water have a tendency to absorb sunshine. So absorbed sunshine will lead to more melting. So there's a positive feedback loop which is important for climate science. Of course, melt ponds are also useful for the phytoplankton activity under ice. So biogeochemists care about these objects also quite a lot. So I'll just briefly mention these two geometric characteristics which you have seen already in Predrag's talk. First geometric characteristic is power law scaling of pond size distribution. So this is reproduced from Don's paper in 2002. So he has taken a look at a few dates and analyzed the image to get this probability distribution function of the pond size. You can see that for a wide range of dates, actually, this distribution appear to fall on a universal curve with a universal exponent. And he found that exponent is about minus 1.5. Right, this is the first geometric feature. Second geometric feature is done by Ken's group. So second feature is that as the pond size increases, the local fractal dimension will actually increase from 1 to 2 around the critical area of 100 meters squared. So on the left is a scatter plot of area versus perimeter. On the right is the fractal dimension computed using a suitable method. And you can see that fractal dimension increases from 1 to 2 right around 100 meters squared. And you can see the shapes of these ponds with the fractal dimension 1 is very simple. With fractal dimension 2 is more like a space filling curve. In between you have some sort of more properly fractal structure. Okay. So we want to use Ising model to describe this melt pond. So I'll give you a brief idea of what Ising model is. This is actually a pretty fundamental object in statistical physics. Actually has a long history, almost we're almost at 100-year anniversary of this model. was first proposed in the 1920s. It's a classical model of magnetic material. So this model is actually very simple. It's almost the simplest model that produces this feature of linkage of scale, which is to say, well, you have a lattice scale. There's a small scale here, and then this spin can cluster into a larger scale. So it's a fundamental model for linkage of scales. So this model parameter, we care about lattice, a regular lattice. You can take it to be square or a cubic lattice. And on each lattice site I, you assign a spin variable. Spin variable can be either up or down. Up is +1, down is -1. And usually for magnetic material, you want to ask yourself, well, how strong is the magnetization? So magnetization is just the mean of all the spins. So sum of the spin divided by the number of lattice sites. All right. So how the game goes for the Ising model is that these spins will interact each other by a so-called coupling strength J. And meanwhile, these spins are also influenced by an external magnetic field H. So this coupling strength will tend to, well, depending on whether it's positive or negative, will tend to make spins either align or anti-align with each other. And so, so actually, with these conditions in mind, you can just remember that the overall goal for the model is to minimize this quantity here, which has two terms. So you can see from this expression that if J is positive, for example, if you want to minimize this quantity, you want these neighboring spins to be pointing in the same direction. And the first term tells you that, well, for example, if H is positive, you want your spins will tend to line up. So this external magnetic field will give you a preferred spin direction. Right? So first term gives you preferred spin direction. Second term gives you a clustering effect. So this is the simplest version of the Ising model. So actually, for modeling melt pond, we want a slightly more complicated version. It's only slightly more complicated in the sense that we just want the magnetic field, this coefficient H and J, to be possibly dependent on the location, right? So this is the slightly more general form of the Ising model. And for melt ponds, we identify these spin variables as corresponding to meltwater or ice, depending on whether it's positive or negative. So these parameters, H and J, represent space-dependent magnetic field and coupling constants. You may ask what they mean. Well, we will talk about their physical meaning in a few slides' time. So if you are familiar with statistical physics, you may also remember there's a quantity called temperature T. So in the previous slide, I mentioned the goal is to minimize H. So if you have a non-zero temperature, you minimize H in a stochastic sense. So you kind of wander around the minimum. But in this talk, we actually set the temperature to be 0. So we do want to literally minimize H. All right. So to adopt Ising model for melt pond, actually we would want these coefficients Hi and Hj to be random variable. If you choose them just to be constants, then you don't generate too much pattern, right? So the particular case we're interested in, we actually do want the j's to be constant. We want the h to be independent random variable. So then the key idea is that we are identifying complex Arctic melt ponds as a simple disordered system. So as Project told you, this complexity of this model is also about there, I guess, on the same order of magnitude of complexity as his model, because this model also has very minimal set of parameters. All right. So so how this minimization of this free energy goes? So we would want to minimize the free energy H. So we actually want to start from a certain configuration of spin, and then we try to change this configuration and see if the quantity H decreases or not. So this is pretty much similar to this gradient descent method you may encounter in optimization. But this is a discrete version of it, of course. So you attempt to flip the spin, and if you find that the spin flip causes the quantity h to decrease, you accept the flip. Otherwise, you reject this flip. And this kind of dynamics has a name called Glauber single spin flip dynamics. So following this dynamics, you start from a certain spin configuration, and you eventually be guaranteed to converge to a local minimum of h. Of course, you know these methods don't give you a global minimum. There's no guarantee that any method will give you global minimum. But local minima are actually quite prevalent in nature, as you'll see in the next slide. So these local minima are called metastable states. These are actually pretty often observed in nature. Actually, two of the most famous examples include supercooled liquids. Actually, even this is quite relevant to melt ponds, as seen from talks in the previous couple of days. And also in the atmosphere, aerosol particles are also identified as a metastable state. So it has some relevance to climate science. In fact, if you consider Earth as an entire climate system, the Earth may also be in a metastable state. So here's just a simple mechanical example. So if you consider a ball rolling on this landscape, if you place the ball at some point, like right here, the ball will happily stay there. Of course, it would be mostly stable. It would be happiest when it's in that state. But if you put it in that state, it's not going to roll anywhere else. It's going to be locally stable, right? Of course, if you put it in any other point, the ball will fly off. All right. So these metastable states are really quite often observed in nature. Okay. So we come to the actual definition of the model. So this is where the physics comes in. Is that when we consider how melt ponds are formed, what I think most people agree is that melt pond morphology or geometry is predominantly determined by this ice topography, right? So we would want to think of a model that tells you how this pre-melt ice topography will determine the melt pond pattern, right? So this pre-melt ice topography we know is highly non-uniform, and this can be identified as this random variable in the Ising model. So this is really the key input parameter. We assume that you have a pre-melt ice topography given by this random variable hi. So at each lattice site, we assign a random variable, right? This denotes the ice topography. And we take the simplest assumption. We assume this random variable hi are independent Gaussian with zero mean and unit variance. So these random variables hi are pure disorder. They are pure white noise or whatever you call it. And the Ising model really is a recipe for creating melt pond, which is a ordered, pretty orderly system from these disordered variables hi. Right. So the specific rule by which this hi will determine the configuration is the following. So so we consider a lattice, all right? We start from a certain spin configuration. And we try to flip a spin, okay? So we want to have a criterion for when the spin flip is accepted and when it's rejected. Okay, so for example, we divide this discussion into two cases, basically. So you see each side has 4 neighbors, and these 4 neighbors could be, could have different spin configurations, and if a majority exists, namely if a site is surrounded by 3 water sites, then we update this site to a water site. If a site is surrounded by 3 ice sites, we update it to ice. So if a majority exists, we want to update the site to align with the majority. This actually describes the physical process of heat diffusion between these neighboring sites. So I think this is a very physical assumption. And if there's a tie between the neighbors, namely, if you find your spin configuration, well, a particular site has two water-sized neighbors and two ice-sized neighbors, then really we need to make a decision. And that decision is made based on this random variable hi. So that decision is also very simple. So if we have such a situation, we want this spin to be updated according to the value of the random variable hi at this site. So if this value is positive, then we say this site will become an ice site. Right? If this value is negative, then we say it's a water site. So this just describes very basic hydrology, namely water tend to flow onto low places, right? So, so if the ice topography is negative, you would want a water site to fill this site. All right. So this is pretty much it. The model is described by these two very simple update rules. And so, so in a more mathematical form, you can summarize these updated rules as a single expression, right? Or this expression can be matched to the general form of the Ising model. So eventually, the model we are proposing is just a simple special case of the classical random field Ising model, right? You can see that the coupling constants are not location dependent, and the random field is in the first term, right? So actually, we want the coupling constant to be infinity, and this applied magnetic field H is also 0. So this model, as you can see, is actually parameter free, right? You don't need to input any parameter at this stage, right? Okay, so next I'll present some numerical simulation results that this model produces. And so to facilitate observation with geophysics literature, this order parameter will take as the Pond fraction. And so it's the fraction of the up spins. And it's related to this so-called magnetization by this formula. So if the magnetization is all -1, then that means the Pond fraction is 0%, right? And if the magnetization is +1, Pond fraction is 100%. Okay, so this is the setup of the model. So I'll just describe briefly how the numerical procedure goes. So numerically, how do we implement the model in order that it creates order from disorder? Okay, so these numerical results are presented following this global dynamics of the random field Ising model. And so we take 10 Monte Carlo steps, so which means that on average, each spin is attempted to be flipped 10 times. So this will enable the system to converge onto a metastable state. Lattice size is taken to be pretty big. So actually, we want the input spin configuration to be also a random spin configuration. So this is actually a parameter that we do need to put in. So basically, it's like that. It's like you tell me how much pond you want to produce using this model. And if you want more pond, I'll start from a spin configuration with more up spins, all right, and vice versa. So you start from random spin configuration, and then you follow this spin flip dynamics, and eventually you generate a metastable state with a certain output Pond fraction, all right? So here we have introduced just one parameter, the input Pond fraction. And by tuning this F in, you can get different values of F out. Where does it stop? Okay. Okay. This connection is a little unstable. Okay, there you go. Hopefully it stays there for a couple more minutes. All right. So here are shown some numerical simulation results. So you can tune the parameter to achieve different output Pond fraction. And so here are Pond fraction 15%, 30%, and 45%. You can see that these pictures actually do look visually quite like real melt ponds in a sense, right? So basically, we are identifying melt ponds as metastable islands of like spins in our Ising model. All right. Okay. So these are the model outputs. Now to connect the model to observations, we need to introduce this length scale, which is the lattice constant. So remember that the statistical physics model illustrates how an initial snow or ice topography gives rise to melt pond later on in the melt season. And so we want to extract this length scale from the initial snow or ice topography. Right. So here's a picture of the snow topography in the beginning of the melt season. So we want to do some data analysis on this snow topography. And lattice constant is extracted this way. It's defined as the length scale above which important spatially correlated fluctuations occur in this power spectrum of sea ice topography. Okay, so you see where it is going. We are taking this ice topography data and we are computing a power spectrum. And we want to look at what scale this power spectrum exhibits some unexpected feature. So these wiggly lines are the actual data processing results. And these solid lines actually best fit with what's called a null red noise spectrum. All right, so you can see that this power spectrum density follows the red noise up to a certain length scale. And this length scale is taken as our lattice constant, is taken as our microscopic, namely the small scale in our model. All right, and this lattice constant is found to be 0.85 meters. This is from the Sheva project. Right. So with that in mind, we will finally produce predictions on this geometry characteristics. So we can analyze the model output and we can figure out the probability distribution function for the pond size. So on the left is the result from the paper almost 15 years ago. And on the right is the model output from the Ising model. And what's remarkable is that the exponents actually agree really well. Model output is about minus 1.58 and the observation is about minus 1.5. So these agree really well. So I think this is a strong indication that the model is on the right track. So another indication a model works really well is we can look at this transition in fractal geometry. So the fractal dimension can be computed for the observation and also for the model output. So the model output gives you a transition area of about 70 meters squared, whereas the observation is about 100 meters squared. You can see these two curves, two transition curves, actually agree not only in the center of transition, but also in the width over which the transition occurs. Well, transition occurs over about 2 orders of magnitude. So this width is also reproduced really well between the observation and the prediction, right? So we have presented 2 pieces of evidence that the model works really well. Okay, so here is just a summary of what we were able to achieve up to now. So we have proposed that this classical random field Ising model can actually describe this complex geometry of Arctic melt ponds pretty well. Well, only assuming a minimal set of physical parameters. So basically, the only 2 physical parameters we input are actually pond fraction and the lattice constant. And the lattice constant actually came from analyzing real ice topography data. So in a sense, that's why this model is actually more physical, and I think that's an advantage, of course. So we are able to predict 2 things. One thing is the scaling exponent of the area probability distribution function. The other is the critical area for the fractal transition, or the onset of complex pond shapes. So some future directions, when we talk about a physical model such as the random field Ising model, you can proceed to look at more physical effects, how they can be incorporated. So ice albedo feedback, you can easily, well, not too easily, but you can incorporate it into the Ising model by taking this coupling constant to be proportional to this pond fraction, right? So that means if the pond temperature increases, the tendency to cluster also increases. So this physical effect, you can put it into the random field Ising model. Some other directions in relation to global climate models, you can use the Ising model to provide a suitable parameterization scheme. And we're also looking into how you adapt this approach to other interesting objects such as permafrost lakes. Okay, so I'll end here and thank you for your attention.
Thank you. So we got time for some questions before coffee. Right?
The previous speaker seemed to be suggesting that these statistical measures like fractal dimension are just sort of universal features. And so is this Ising model simply a way of throwing the dice?
Well, I think throwing the dice.
In other words, you know, is the physics
it's a very elaborate way of throwing the dice. It's actually a very, yeah. So I think a good thing. Well, we are able to predict these particular geometric characteristics, right? So just a random dice throwing model would not give you these characteristics that well, I believe.
Well, that's the question.
Yeah. Yeah.
Have you tried other ways?
I mean, as far as Ising models are concerned, I think this is about the simplest model we can come up with that still predict these features reasonably well. So we have reduced as far as possible the physical parameters. The input parameters are really just a very minimal set, and yeah, and the predictions are still quite good. And actually, yeah, we were able to connect these quantities with physics, such as these snow topography. We were able to analyze the data and extract a certain length scale from there. So I think there are some advantages here. Yes.
In your model, I think that what I'm confusing is there is a box, you know, that shows up and down in the spin. In the case, there should be a size of the box which is equivalent to real length scale of the CIZ.
Right.
Can you guess what that is? And second, you are going to evolve that model.
Yeah. This is the so-called lattice constant. Lattice constant is the size of the box.
Yes. So
Yes.
what is the? It's what, 100 meter? Or?
No, it is 0.85 meter. It is this small length scale. Yeah.
Okay.
So the key thing that this model does is we assume that this lattice constant is a small scale, and we are able to use the Ising model to generate larger scale pond pattern. Right. So the small scale is this 0.85.
And then to reach the equilibrium, you need a time scale. What is that?
Oh, okay. So to reach equilibrium, we follow this so-called global dynamics, right? So normally we wouldn't associate global dynamics as a time evolution. So this is basically a device through which you reach the metastable state. So basically, okay, here we on average attempt each spin flip 10 times. Right? So this will be mostly enough for you to converge onto a local minimum of this free energy.
So in the case, you think in the real field, melt pond,
Yes.
always find the metastable point quite quickly. So
Oh yes. Actually, if you talk about the real physical time, yes, real physical time. We have an estimate of how this spin flip will happen. So the spin flip, actually, if you think about it physically, it happens by radiation balance. So so this part I didn't mention in the talk, but basically you have incoming shortwave radiation, right, and outgoing longwave radiation. So if a site is an ice site, then the ice will tend to continue to grow, and vice versa. If a site is a water site, water will also continue to grow. And so the time scale on which this growth or decay happens is actually about 10 to 15 days, right? So basically, you have this intensity of sunshine, and this sunshine will enable you to melt a certain ice column of height maybe 30 centimeter in a matter of 10 days, 10 or 15 days. So actually, yeah, actually this is also a very physical point that you made, that this spin flip actually takes place on a time scale of about 10 to 15 days, is well within a single melting season. So in a single melting season, well, there's plenty of time for the system to find a metastable state. So yeah, so that's why I think this model could work quite well. That this spin flip actually happens pretty fast. Yeah.
Okay, well, let's thank our speakers for this afternoon. Thank you very much.
Thank you.